Good afternoon to everyone. I'm Carlos Garrido. I'm a PhD student at the University of Alicante, and I'm going to present our work, a holistic approach for image to graph and application to OMR. Okay, so to give some context, optical music recognition, as you may know, studies how to computationally read music notation from music scores. Current literature applies techniques to obtain sequential notation, but given the relational nature of the music notation, some authors have proposed to model this notation as a graph in which the symbol or musical primitive represents the notes and the relationship between these symbols represents the edges. To give some background on the related work of our work, there is extensive literature of the processing of graph as input, but little work explores inference of graphs conditioned to a given input. And the areas that are most related to our work are deep graph generation, in which a generative model, neural model, generate graphs, which can be in one shot forward pass, or iteratively generating the sequential graph. But in this case, we need to learn a discriminative model. And the other one would be sim graphs, in which the objective is to extract and construct graphs to model semantic relationships between entities. But ideally, we want to use methods that have this spatial information available. Okay, so moving on to our approach, we formulate this task as an image to graph, in which we have to retrieve the most probable graph over all the space of graphs. But we have a main issue. This representation over the this representation of a single graph is given by the factorial of the nodes that is computationally unfeasible. In this work, we approximate the solution with the graph with the most probable representation. How can this be achieved? We assume a function phi that maps a graph G into a representation R that mainly transforms a set into a sequence. And this transformation, makes it possible to treat the extraction of the nodes as a sequence retrieval. And then we jointly minimize the multi-loss of the cross entropy of the nodes and also the binary cross entropy for the adjacency matrix retrieval. We represent the relationship between each node. Okay, so for this approach, we propose a convolutional neural network plus a recurrent neural network based architecture with the visual attention mechanism. We perform jointly both tasks, the node extraction and the releasing extraction, as can be seen in the figure. We process music excerpts convolutional neural network, and then for each time step with the hidden state of the recurrent neural network that represents each node, we do a pairwise grouping, and then we predict whether it's a relationship or not. Okay, for the experiments, the dataset used was the MuSchema++. It contains handwritten music notation and is composed of 114 music scores, more than 91,000 symbols, and more than 23,000 notes. We, as I have said, we use music excerpt as input, and as can be seen in the histogram on the right, graph sizes range from 4 to 27 nodes, and the primitives selected for the experiments were full and empty node heads, stems, genes, and 8th and 16th flags. For the experiment, we consider the following evaluation scenarios. First of all, the function phi choice, whether it's topological or alphabetical. Topological means that the nodes, in order to start the sequences, topological is as they appear on the image, completely from left to right and from top to bottom, or alphabetical, that means that are simply sorted in an alphabetical way according to the vocabulary. The other scenario they want to test is the visual attention mechanism. And also, as you may know, in OMR, there are not many data available, and we also wanted to see the performance of the models under under extreme data constraints. Computing graph distance is an NP hard problem, and for this reason, we use two metrics. The first one was the symbol accuracy, calculated as 1 minus the symbol error rate, and the other one for the scores for the edges were the F1. Moving on to the results, in this figure we can see the test results for both symbol accuracy and F1. With respect to the symbol accuracy, we see that the models providing the best results are the one with alphabetical order, specifically with the visual attention mechanism, followed by the same one with no attention mechanism. With respect to the F1, we see that the same results are repeated, and the best models are those with the alphabetical order. As a model discussion, given the images and all the possible rotation that they can have, the models with alphabetical order always have the same consistency and allow learning in a simple way. Also, it is important to note that even with extreme data limitation, like for example 5 and 25 data percentage, they work well. We have seen that the results are generally good in terms of symbol and F1 accuracy. However, in isolation, it does not mean that a good symbol accuracy allows us to obtain the relationship well. In order to know if there is correlation between these metrics, for example, getting the node right allow to get relations correctly, we show in this figure the correlation between these two metrics in the test set for all the faults. As can be seen, they are indeed correlated with an R coefficient of 0.99. For giving some visual results, we see two figures here, and in the first one, in A, there is an example of accurate prediction in which nodes and edges are retrieved successfully. It's important to note that for training and testing, we don't use the bounding boxes. And in figure B, we see that neither the stem here on the left nor the and stem and nor the stem is detected correctly, and also there is a false positive in one of the relations, the left one, of the node head to the beam. Okay, here we can see where the model is looking for different nodes. It can be seen that models with the visual attention mechanism know where to focus to correctly extract the corresponding nodes in the sequences. Okay, to sum up, in this work, we proposed a holistic model to convert from images to graphs. Our solution is based on a sequential classification of nodes and pairwise relationship reconstruction. It is successful formulation in the context of musical excerpts. And we have seen that we can retrieve the graphs without special information about the elements. As a future work, we plan to retrieve graphs from full pages. We also want to compare our method against state-of-the-art OMR systems. We would like to create in-loss functions or to use neural architectures that are independent of the sequence order, like for example, deep sets, etc. And we want to test our approach in other document analysis tasks, as for example, in equation retrieval, etc. That were the references used in this presentation. And that was all. And thank you for your attention.
Thank you very much, Carlos. Right on time. We have about 7 minutes for questions. So anyone, any question? Okay, Paul?
So first of all, congratulations, because this is a really interesting work. I was wondering, however, in one of the examples, so have you... I cannot hear you correctly. Excuse me, I cannot hear you correctly. Can anyone else hear me well?
No, okay. It's very difficult. The sound is very muffled.
Oh, okay. I think I have a configuration issue. So if there is another question, I will have to go outside and in the room.
Maybe you could pose the question in the chat because
Yes.
it's difficult to understand. Okay. Any question in the meantime? No. I guess I can go for a question. So my question is, why was MuSchema++ used? Are you using the among relationships?
Yes, I think MuSchema++ was one of the only dataset that has this relationship and labeled. So that's mainly was the reason to use the MuSchema++.
So so these relationships are the most you can do because if I remember right, there's not a lot of relationships in MuSchema++ as it is. So your relationships are also constrained to the same relationships.
Yes.
Okay.
Yes. Yes.
Thank you. Paul, you can pose your question now.
I think you should hear me well now.
Yeah.
Yes. Yes.
Okay. So first, congratulations about the work. And my question was directed to the fact that right now you don't make any differentiation between node heads or elements within the symbol complex that you're recognizing, right? Hence, my question was directed to the fact that, are you considering permutation invariance? So for instance, if you have two 8 nodes together joined by a single stem, regardless of whether your model assigns one or the other to the same stem, it will result on a permutation invariant graph. But how is this dealt with? Do you enforce an order in the loss on the matrix or what?
Yes, thank you for your question. Okay, so I'm moving on to the concretely to the loss function here. Yes, so I have said in this work we assume a function phi, and that is the constraint to so for the model to extract the order sequence. So it's not permutation invariant because we are constraining the model to completely get a single possible sequence. That depends on the function phi.
But I'm referring to the adjacency matrix of the model, because then all the nodes are basically the same, have the same meaning. But,
Yes.
And then they can be arbitrarily joined to any stem so long as the final adjacency matrix is the same. But how are you dealing with permutation invariances within that space?
We are not dealing with that. The adjacency matrix is also constrained by the to the sequence of the nodes.
Because I was thinking that maybe it would have been interesting to see some kind of CTC-like approach where you basically take that into account, all possible reconstructions of the same adjacency matrix, but with the set of nodes that you have predicted. And that was it. It was just an insight. But thank you very much. It's really interesting.
Yes, thank you.